Well, hello. We'll pick up on the next lecture here. So this is material after exam two. As you can see from my background and the lighting is going to be different. I'm on a not my normal home office slash studio. So we're going to make the best of the situation. Oh, I'm in a Airbnb. Kind of has a bit of a log cabin feel to it. It's a really nice place though. All right. I'm gonna put out a couple of videos this evening and move forward. So again, this material will be after exam two for me and for my students in my class. We've just taken an exam on the first law of thermodynamics for both steady flow control volumes and stationary closed systems. Now we work our way towards material where we start analyzing and looking at the second law of thermodynamics for different types of systems. So, in most thermodynamics textbooks, you're going to find something kind of like our chapter six that we see in our textbook, where we introduce concepts of the second law. We talk about some of the history of how the second law came to be, and then the next chapters, a lot of times in the textbook, then we actually dive headfirst into looking at the second law, quantifying it, calculating entropy balances, things of that nature. For us, in the Changle and Bowles text, that would be chapter six is kind of the history and how did we get to the second law. And chapter seven then is the actual second law, where we do some entropy calculations. So, with all of that said, when we get into the second law, there are processes or devices that we could build or things that we could propose that they don't really, sorry, they don't really, these are not things that are possible. Um, they may not, well, let me just give you an example. So they're different processes or what we call perpetual motion machines. That was the word I was taking for there. There are things that we could propose that just aren't going to happen. But what you will find is they might not violate the first law, or they might not violate the second law, but they will violate the other one. This is one of my favorite examples. So, you come over to my house, and I set out on a coffee table a can of Coke, and I'm from Central Oklahoma, where almost all doesn't matter what flavor it is, it's all Coke. Do you want Dr. Pepper, Sprite? What is it? Well, it's all Coke to us. Um, so we take out a can of Coke or whatever your favorite beverage is. We place it on the coffee table. Let's say it's already slightly cooler than the atmosphere, but you know what? Spontaneously, that thing is going to lose 10 degrees Fahrenheit to the atmosphere. It's spontaneously going to get cooler. Now, you know what? Here's the thing. The first law does not care that this is not going to happen. The first law says, you know what? As long as that thing doesn't create or destroy energy, as long as the amount of heat that can of Coke loses is essentially the amount of energy, the internal energy drop of that can of Coke, go for it. That is just fine. This is an example of something that we could propose. Hey, this is a thing. We could have these magic cans we just set out on the countertop. They magically lose 10 degrees Fahrenheit, and I could apply for a patent for that. And there was a time where, that I might actually get a patent for that. It was an idea, and I just would have a certain amount of time to figure out how to actually do it and make money off of it. What we know today is this isn't going to happen spontaneously. Okay. This process may not violate the first law. It is in violation of the second law. Realistically, it's going to do what we call destroy entropy for this to occur. Um, how do we quantify that though? Because before we really had a way of quantifying and understanding the second law, we had to try to figure out, okay, well, we don't think we could do something like that, but how do we know we couldn't do something like that? So what you find is you have a lot of scientists and engineers studying, especially devices like steam engines, but also refrigeration cycles, and all around the time of the Industrial Revolution. Okay, I'm not a history buff, but believe we're talking 17, 1800s in this time frame, where we have these devices where we can extract massive amounts of energy from heat. and power our facilities, our factories, our textile mills, our locomotives, our different machines. And we want to get the most we can out of those. One such individual is Rudolf Clausius, a German physicist slash engineer that is instrumental in the development of the second law. One of the grandfathers of the second law. Now, Klaus is working with some steam engines, trying to get the most energy he can out of them, comes to the conclusion you cannot construct a device operating in a cycle that has no effect other than moving heat from a lower temperature body to a higher temperature body. It's not going to occur spontaneously. It doesn't mean you can't do it. It just means it can't be the only thing your device is doing. Now, as I said, most texts are going to have some chapter kind of like chapter 6 in the Chamberlain-Bowles text, where we're really going to dive into the history of how did we come to understand the second law. So the Clausius statement, which we just mentioned here, is one of the fundamental bases that is used to formulate the second law. Another fundamental basis is what we call the Kelvin Plank statement. So as I understand it, both Kelvin and Planck are scientists slash engineers working independently and almost in the exact same time frame come to the almost exact same solution, completely independent of one another. So we credit both of these individuals with this observation, with this statement. And they come to the conclusion you cannot construct a device that its sole purpose is receiving heat from an object and producing a net amount of work. Now, what that means is, for example, right, if we've got a power plant and we've got steam coming out of that power plant, and we run that steam through a turbine or a turbine. Well, through the turbine, that steam is going to get expanded, and as it expands, the pressure is going to drop. Okay. Now, if I take that steam and I heat it back up, that steam's going to expand a little bit. There's really nothing in that expansion or I'm sorry, there's nothing in that heating process that's going to cause the steam pressure to increase. I'm going to have to put some work. I'm going to have to squeeze it to get that pressure to increase. Um, but if I just heat it up, it's going to expand a little bit more. And then if I run it back through the turbine, the pressure's going to drop and it's going to expand even more. And then I'm going to heat it back up a little bit and I'm going to run it back through the turbine a little bit more, and eventually it'll expand to the point after I run it through the turbine enough times, it'll expand to the point where there's nowhere left for it to expand. Um, and I all the while I can't operate in a cycle, meaning I can't get back up here to this initial point, right? Um, and that's what Kelvin and Planck is saying. You can't operate in a cycle, meaning you can't operate as long as you can maintain it. We won't say perpetually because that's not a way to describe this, but you won't be able to operate it. I mean, you could say perpetually so long as you can maintain the inlets, but we're not going to be able to get it to repeat over and over again in a cycle in by doing something like this, where we run steam through a turbine, we let it expand, and we heat that steam back up, and we run it back through the turbine, and we heat it back up, and we run it back through the turbine. Kelvin and Planck come to the conclusion you can't do that. You can't just keep applying heat from one body, one reservoir, and continue to operate your system and expect it to operate in a cycle. You're going to have to basically close the loop. You're somehow going to have to get back up here to your initial state in order to operate a cycle. And you're not going to be able to do that just simply by absorbing heat from one single body. Right? So that is the Kelvin Planck statement, the conclusion that they reach. And you take observation statements, conclusions, kind of like the Kelvin Planck statement. You take the Clausius statement and you put those along with the works of other individuals all during this time of the Industrial Revolution, and you put it all together, and that's how we come up with what we understand today of the second law. Okay. Now, how do we quantify those? Those are just statements, right? Those are just quotes. So how do we quantify that? How do we get that into a useful format? Well, as engineers and scientists and people in STEM, we often want to be able to have some concrete quantification. Um, and so that's there that exists. And I always like to say chapter six for us is the second law without ever actually showing you the second law. It's just this introduction to the second law. And then chapter seven, we actually show you the second law. This is the second law, right? In its purest, rawest differential equation, or actually differential inequality form, this is the second law. Right? Now, just like any other differential equation, we're going to have to get that down to something we can actually apply to a specific solution. And this is often what we're doing over here on the right is this is the second law as we apply it to a process from state one to state two, which is normally most of what we're going to work with in an introductory thermo course. Is going to be a process from state one to state two. So the form on the right is normally the form that we're going to see and work with. But again, that's chapter seven. Let's talk about chapter six. So, um, again, just a little bit more here. The second law essentially helps us identify what is possible, what actually can happen, what can we expect, what is the limit. Again, it's an inequality. That inequality sets a limit we can't exceed to the best of our knowledge. So it controls the direction that we can actually make energy move. We talked earlier about I can't just sit a can of Coke out on the coffee table and it's not going to spontaneously, I mean, I can set it there, it's not going to spontaneously lose 10 degrees Fahrenheit without doing something else to it. Now, it's possible to cool it down, but something else is going to have to be involved in order for that to happen. It's not going to do so spontaneously. So the second law dictates through that inequality the direction that energy can flow, because the first law doesn't dictate what direction it can flow. It just wants to know, hey, did you destroy or create energy? As long as you didn't, the first law is happy. Second law is a little pickier. The second law, again, because it's inequality, also sets a limit on how much we can do, how efficient something can be. No process is ever going to be more than 100% efficient according to the second law, the way it's set up. And actually, it's often going to be less than that. And the S value you saw, if I go back again, those S values, that's what we call entropy. You see those in the property tables for water and R134, and we've got ways of quantifying entropy for ideal gases we're going to talk about. But that is how we're going to quantify these limits. How much can we do with energy? So the two laws are going to work in tandem once we get there. Now, before we actually jump off the deep end and try to begin quantifying entropy and figuring out how far can we go along that limit, let us talk about some of the theory and some of the terms associated with it that we need to understand before we get there. And again, that's kind of the whole focus of chapter six is understanding how the second law works and how we got there before we actually talk about, before we actually get into the second law. Now, so one of the terms, a very important term that we need to understand here is what we call a thermal energy reservoir, right? So a thermal energy reservoir is just simply a body or an object or a mass of some kind that can absorb or supply finite amounts of energy. Not infinite, finite amounts of energy without undergoing a significant change in temperature. It's pretty rare that I'm going to use this full term with all the adjectives, the thermal energy reservoir. I might use reservoir, I might use heat reservoir, thermal reservoir occasionally. I will normally use the term source and sink, which I'll introduce in just a second here. But thermal energy reservoir is the technical term, completely correct. And what does that mean? Again, that's something that can absorb finite amount of energy or supply finite amounts of energy without experiencing a major temperature change. So if my system is reasonably small, right? If this is my system, for example, if my system's reasonably small compared to the things that are representing energy reservoirs. Those are normally good candidates. Things like the atmosphere, things like a large body of water, a lake or a river, or possibly an ocean. These are places where we can actually put large amounts of energy, or we can again extract large amounts of energy. And compared to our smaller system, these are not going to experience a significant temperature change. Right? Now, we do have to be aware that, and there's going to be limits as to if I set, say, a nuclear power plant next to a lake or a river, there's going to be limits as to how much heat or how much energy I can dissipate into that energy reservoir, that lake or that river, because the marine life, the aquatic species that are there, they've evolved over millions of years often, and they're not going to be able to quickly um, adapt to significant changes in temperatures. We have to be aware of that. And there's going to be limits set on that. And with well, let's just say who knows what that future is going to look like, but that is something we do have to be aware of. All right, I have hit my 15 minutes on this video. I'm going to stop this one and we'll pick up the next one.